In this lesson, we're going to talk about relations and functions. A relation is a set of input and output values. Relation can be written as a set of ordered pairs. So these are most known as coordinates. Right? Our input is our x, our outputs are y, and we have a little coordinate point of x, y. Domain. The domain is a set of input coordinates or x coordinates of ordered pairs. So this is our x values. The range will be the y values. The set of output or y coordinates of the ordered pairs. Function. Function is a relation in which each element of the domain is paired exactly with one element of the range. So again, in this case, otherwise known as each x value is unique. So you won't have like two x values. You can have two y values, but each x value should be unique and different. Okay, so let's do an example. Let's just talk about how to recognize the domain and range. So in this example, we have a table where x values are also known as our inputs and our y values are our outputs. And all these are coordinate points. Like this point right here would be the point 1, 11. And this would be like 3 and 13. And so on. So I want to write the domain down. We're just going to list all these x values, all these inputs. So like this. We tend to do curly brackets when we do a list. So it'll be 1, 2, 3, 4, and 5 will be my domain. My range will be all the y values. So that's going to be 11. That's an ugly bracket. 11, 12, and 13. You don't need to rewrite the same thing over and over again. So there's 3 13s. That's fine. That's all my range. So that's how it is. What if I gave you a list of values, right? This is a list of coordinates. So this is the coordinate 0, -1, 2, -4, right? Same idea as the table, just written differently. Well, same concept. My domain will be the x values. So all the x values will be right there. We want to try to write it in proper order. So lowest first, so -4, then 0, then 1, then 2, then 3. And the range will be all the y values. And then same rule. I'm going to try to write it in order. So lowest would be -4, then -1, then -2, then -1, then 3, then 5. So that would be my range. So that's how simple it is, right? Just domain is the x values, range is the y values. So let's move on. Next, let's analyze domain and ranges. We're going to talk about continuous versus discrete. So continuous means your values could be all real numbers, while discrete means you can only have a certain set of numbers. So just whole numbers or integers, like it has to be a certain set. A good rule of thumb is continuous is something you can measure, while discrete is something you could count. An example of each, count would be like the number of songs on a playlist. Right, that's something you could count. So that'll be discrete. Something that's continuous would be the length of a song. Right, you can't count that. You have to measure it like in time. So that's an example of continuous versus discrete. Let's look at a couple more. So in this graph here, we have volume according to time. So how much volume is in like a swimming pool compared to time. Volume is something you have to measure. If you want to figure out like how much water is in the pool, that's something you're going to measure. So this is continuous. And that's why you see the lines connected. When it's continuous, you could be any value. So the lines are all nice and connected. So it's going to be nice. It's going to be connected line. With something discrete, like the number of, let's look here, number of tables and number of chairs, that's something you have to count. You have to count how many chairs and tables we have together. So you can't have like 2.5 tables or 8 1/3 chairs. It doesn't make any sense. So this would be discrete. If you notice, it's not connected. Okay. Next. Is the domain of each situation continuous or discrete? Explain your answer. So the number of concert tickets that can be purchased. So you just gotta think, could I buy a third of that, a half of that? Could I go like 2.3? You can't buy 2.3 concert tickets, and this is discrete. You must buy whole tickets. Next one, the number of pounds of grapes that can be purchased. So when you buy grapes, you don't pay for each individual grape. It's like they say, the number of pounds of grapes you're buying. So this would be continuous. Again, we're talking about the pounds of grapes. That's something we can measure. They're not just counting grapes in general, which would be discrete. The pounds of grapes. Next, let's talk about something's a function or not. So remember, when something's a function, all x values are unique. So all we care about is the x values. They all have to be different. So let's look here. Here's an example, right? My x is all we care about is the x. So we have 0, 2, 5, 1, 4. This would be a function. On our next one here, we have 0, 2, 1, 1, 3. So this would not be a function. Because right there, right, we have 2 1s. So this is not a function. So that's how you tell given like lists of points. You just look at the x values, it's all different. Sometimes what we have, well, right, is what we call a function map. Something like this, we're letting you know, okay, in the domain, 1 goes to 6, 2 goes to 4 in the range, 3 goes to 5. So again, this would be like our x values and our y values. Same concept. Are all the x values different? So in here you can see, right, they all go to a separate thing. So this would be a function. And we want to this example here. Hope you see that 1 goes to 4 and 1 goes to 6. Like if I was doing points, this would be 1 4, 1 6, 2 5, and 3 5. So if you notice, that 1 right there goes to two things. It goes to 1 and it goes to 6. It's a little 2-timer. So this is not a function. Again, we only care about the x in that case. So all we care about is the x's. Y's can do whatever they want. X's have to be one. It only has to be one of each. They can only go to one x. What if I gave you a graph, right? We determined it was a function if I gave you points, if I gave you a mapping. Next up is what if I gave you a graph? Well, there's an easy shortcut to doing it, which is the vertical line test. So same concept, right? We want all the x to be different. So an easy way to tell on a graph is what's called a vertical line test. If a vertical line can be drawn that passes through at least 2 points on the graph, then one of the elements in the domain is paired with another element of the range, therefore direction. Okay, that's a lot to saying. Easiest way to tell the vertical line test, you fail it, which means you're not a function. If it crosses twice, 2 or more. Right. So the general idea is we're gonna draw vertical lines, and if you hit the graph more than once, you fail. So you're not a function. So let's do a few examples. So like here, right? I'm just gonna draw vertical lines. And no matter which one I draw, I'm only gonna hit the graph once, right? They all hit the little points here one time. So this is a function. It passed. It passed the vertical line test. If I look over here, it's gonna fail it if I draw a line right there. You see there and there, you hit the graph twice. So this fails. So it's not a function. So that's with discrete data. Let's do continuous data. Same concept, right? We're gonna draw vertical lines. Now they have to be straight up and down, right? And in this case, I didn't hit anywhere more than once. So it passes the vertical line test, so it's a function. And if you look at the next one, we're gonna have problems. Lots of places. If I do it here, if I do it there, all these places I hit more than once. So it fails, and it's not a function. So that's how you tell something's a function. If it's a graph, the easiest way to do it is vertical line test. It's the same concept though. It means you can't have two of the same x's. So when you have a mapping, just look all the x's, right? If any of them double up, it's not a function. That's all we care about. That's what a function is. All the x values are unique. Okay, let's go into the next thing. Okay, let's classify our relation to functions. So look at this first question. Is each relation a function? We know that's a no, right? We have functions, we have relations that are functions, some relations that are not functions. And it's the same thing with types of functions. Not all functions are the same. Some of them are one-to-one, some of them are not one-to-one. So what does one-to-one mean? Well, first, let's go back to what a function means, right? A function, x value is unique, right? So all of them are different. A one-to-one function is actually very similar. It's a function, so it means all the x values are unique, with all y values unique also. So it's a special type of function where all the x's and all the y's are different. So like none of them 2-time on each other. They're all separate. That's what makes it a one-to-one function. All other functions are not one-to-one. So let's look at an example here, right? So 1, 2, 5, 6, 7, -1, 8, 0. So if you notice all the x values, they're all different. So it's definitely a function. Then if you look at all the y values, they're also all different. So it makes it a one-to-one function. Now, you have the same x and y. Like you could do 1, 1, 2, 2. That still counts. Just all the y values are different from each other and all the x values are different from each other, just to be clear. And then look at our example here, b. Right? If you look at b, 1, 2, 3, 4, they're all separate. So this is a function. But if you look at 17 and you look at 10, there's two different values for y there. Like if we made this a point, it would be 1, 17 and then 2, 17, right? So again, still a function, but not a one-to-one function. It's just a basic function. So we look here, so give two more examples. This one, well, this one's not a function because look at the 3. There's a problem, right? We would have 3, 6 and 3, 7. So that's not a function. Over here is the function, and it's one-to-one. How can you tell if it's one-to-one? Much like you do a vertical line test. If you look at it from the side, kind of do like a horizontal line test. They also don't hit more than one, so that makes it a one-to-one function. So a little shortcut for writing one-to-one. So it's kind of the same idea. You look at all the y's are different, all the x's are different, one-to-one function. Okay, last little concept, constraints of domain. So like what values could domain be? And it changes based on the problem. And this one, we can do a quick example. This shows this diagram here shows the shipping charges as a function of the weight of several online orders. So x is the weight of the order, y is the shipping charge. If any, based on the situation, what constraints, if any, are on the domain function? So what constraints are there on these? So if you try to think about it logically, like, wait, if I'm sending a package, well, the constraint is it has to be greater than or equal to 0. A package can't be a negative value. You can't have like a negative, this thing can't weigh a negative amount. So your constraint is this, x has to be greater than 0. That's it. The next one, Margaret has a monthly clothes budget of $50. She maps out the amount of money she spends each month to the number of items of clothing she buys. What are the constraints there on the domain? So if we're talking about domain as her money, well, a couple things. It says her monthly budget is 50, so we can't go past 50. So we're definitely less than 50. But also, just like how we talked about here, a lot of times your domain can't be negative. We can't have negative money. We don't want to go into debt. We can't spend negative money. So my domain would be that. That'll be our constraints for the domain. And that's the lesson.